Welcome back. In this topic we're looking at groups 1 and 2. Now the first 3 pages of these notes are revision from metallic bonding, also from electron structure looking at ionisation energies. So we're just going to spend a little bit of time firstly going over those pages. So the group 1 and 2 elements are all metals. Together they make up the S block. They're called S block elements because they have their last or their highest energy electron in an S orbital. They all do metallic bonding, and that's shown in this diagram. So you have these layers or rows of positive metal cations and a sea of delocalized electrons. They lose electrons relatively easily to form positively charged ions. As you go down the group, they become more reactive because their ionization energies become less endothermic. It requires less energy. The reason for this is they have more complete inner shells of electrons, which provides more shielding. They also have a larger atomic radius, which means the outer electrons are more easily lost. This is despite the increase in the proton number. Group 1 is more reactive than group 2. This is because the group 1 atoms have a lower first ionization energy. They have a larger atomic radius and they have fewer protons. That means they easily form an ion. We need to remember our first ionization energy definition. It's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Do remember it's always energy required, it's always removing 1 mole, and it's always gaseous. The second ionization energy is the energy required to remove 1 mole of electrons from a 1+ ion. Notice it is not to remove 2 moles of electrons. We can see here that the second and the first ionization energy decrease as you go down the group. It becomes easier to remove the outer shell electron, but the second ionization energy is higher than the first. We can see there the 3 ionization energies, or the first 3 of magnesium. There's a small jump between the first and second as you're removing an electron from a positively charged ion, but there's a big jump between the second and the third. So that's a lot more energy required to remove the third electron than there is to remove the second electron. The reason for this is that the second ionization energy, you're removing a 3s electron, but the third you need to remove a 2p electron. This is from a quantum shell closer to the nucleus, and it's lost a level of shielding. So that electron is going to be held much more tightly to the nucleus. We can use ionization energies to explain why beryllium chloride is covalent, but barium chloride is ionic. Beryllium has particularly high first ionization energies. It has the highest of the S block elements, so it makes it more energetically favourable for it to form covalent rather than ionic bonds. As you go down the group, the first ionization energies become less endothermic. You've got more shielding and the electron is further away from the nucleus because it's in a higher energy level. This also explains why magnesium is less reactive than barium, because it requires more energy to ionize magnesium than it does to ionize barium. It goes on to explain in terms of the melting point. Magnesium has a smaller ionic radius than barium, so despite the fact that both of them delocalize the same number of electrons, there's a greater force of attraction between the magnesium cations and the sea of delocalized electrons. Again, the ionic radii increases as you go down the group in the same trend as the atomic radius. All group 1s react with oxygen. When we demonstrate the reaction of magnesium with oxygen, we need to be very careful to avoid any damage to your retina, which is why we look through cobalt glass. It burns with oxygen to form magnesium oxide solid. And this magnesium oxide is pretty insoluble in water. It will dissolve slightly in water to make an alkali solution. But do remember this process is very slow, so it will take time, but eventually you will get an alkali solution it's actually reacting with the water to form the hydroxide, and it's the hydroxide which is turning the solution alkali. But do notice it's also a solid. They react with oxygen in the same way, barium and calcium forming the oxide. So all group 1s and all group 2s react with oxygen to form the oxide. In the same way, they all react with chlorine gas to make the chloride. So magnesium reacts with chlorine to make magnesium chloride. They react with water, or at least the reactive metals react with water to produce the hydroxide and hydrogen. So we take sodium as our example. It reacts quite vigorously with water to make sodium hydroxide and hydrogen gas. You need to balance it, so we're going to need to work out the different atoms. The easiest way to balance it is to put a half hydrogen, and that now balances. Magnesium, which is the least reactive of the group 2 metals we're going to study, does not react very well with cold water, but it will react with hot water, in other words steam. So we have this little setup here. We've got ceramic wool soaked in water, that's going to provide my steam, and we have our magnesium ribbon in the middle. We heat it very, very strongly until it starts to glow, and then we waft the heat towards the water end to produce the steam, and it'll produce hydrogen gas here, which we can set fire to. Unusually with the metal and water, or in this case steam, we don't produce the hydroxide. It's one of the only ones you need to know where you produce the oxide rather than the hydroxide. So we produce MgO and H2 gas. Calcium is lower down on the periodic table, so it's more reactive than magnesium, so we'd expect it to be able to react with cold water. The reason for this is that calcium has a lower first ionization energy than magnesium, because it's a larger atom, so it's a faster reaction. But notice here you do get the hydroxide. That hydroxide is sparingly soluble in water. Just as a little aside, calcium oxide can also react with water to form calcium hydroxide, and that solution is known as lime water. When you bubble carbon dioxide through lime water, you form the insoluble calcium carbonate, and that's the test for carbon dioxide gas. There are some reactions that you need to know. So you need to know that an acid plus a base gives you salt and water. So an acid plus a base will give you salt and water. So the base we're using in this case is hydroxide. So we have magnesium hydroxide, MgOH2, and nitric acid, which is HNO3. You do need to know the formulas of all your basic acids or your common acids. Magnesium is a 2+ ion, so it needs 2 nitrates. And again, we need to balance it. This will give us 2 moles of water. Strontium hydroxide reacting with sulfuric acid, which is H2SO4, will give you strontium sulfate and again water. Notice we keep the sulfate ion together. Again, makes 2 moles of water. Last one, barium hydroxide, and this time hydrochloric acid, HCl, gives us barium chloride, and again my water. So it's the same reaction each time, hydroxide and acid, salt and water. The oxides can also react with water, again to form the hydroxide, but this time there's no hydrogen being formed as there was with the metal. So magnesium, oxide and water just makes magnesium hydroxide. And that's a solid. So strontium oxide and water is going to give you strontium hydroxide again. And last but not least, barium oxide and water gives you barium hydroxide. Nice and straightforwards. Last but not least, the oxides themselves are also basic, so they can react with acids. So we've got nitric acid, HNO3 again, and again we're reacting to form the salt and water. It just balances slightly differently. Strontium oxide and sulfuric acid again gives us strontium sulfate and water. And last but not least, I've got barium oxide and hydrochloric acid, and that's going to give me barium chloride and again water. So these are some equations you just need to learn. So that finishes this video looking at the first few pages of the groups 1 and 2 notes. The thing to remember is not to learn individual equations, but rather to learn the patterns and the trends. All group 1 and all group 2 elements follow very similar patterns. So rather than learning individual equations, you just need to learn the general equation. So that's all for now. Until next time, take care, stay safe. Bye-bye.